Okay, year 12. This one is 23B, discrete probability distributions. Okay, let's go through some notation. This is actually stuff you've seen before. It's just written differently. So you just got to get used to being confident with the notation, okay, and what it means. So we've got, okay, capital X is your random variable, okay. So let's say it might stand for, getting heads, and your sample spaces, you could get, say, 0 heads, 1 head, or 2 heads. Let's say if we're throwing 2 coins. Does that kind of make sense? So your sample space is like little x1, 2, 3 up to xn. Yeah, it might stand, for example, getting 0 heads, 1 head, 2 heads, etc. And then the probabilities that go with it are going to be like P1, P2, P3, etc. up to Pn. Okay, so that might be like half, a quarter, blah, 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 etc. And so we write it like this. We write it as, capital P, the probability of your random variable x or your event x is equal to being whatever the actual event is, like little x sub I just stands for, one of these ones along here, okay, is equal to Pi, whatever I is, and I is 1, 2, etc., all the way up to n, okay. So that's as simple as me saying like the probability of, let's say x is your random variable. Let's say I want it to be is equal to 1, okay. Head, let's say that we're tossing 2 coins, okay. So yeah, probability of your random variable being 1 is, now what's the probability of getting 1 coin? So remember, if you're tossing 2 coins, we can get heads or tails, right? And then you can get heads or tail again. So you can actually get heads, head, tail, tail, heads, and tail, tail. So the probability of getting 1 is either you can get heads, tails, or tail, heads. So that's 2 out of the 4, okay, which is a half, right? So 2 out of 4, which is a half. So that is a half. So does that make sense that this is the xi, this is the pi, the actual probability, okay? So obviously from the pi has to range from 0 to 1. You can't be more than 1, like 100% chance of something happening. But your total, remember this sigma stands for the sum of all probabilities p, starting with I equals 1 up to I equals n is the probability of your first one, plus the probability of the second one, plus probability of the third one, etc., all the way to your last one, and it has to add up to 1, which makes sense, right? It always has to add up to 1 because that's including the event and like the complementary event as well. Okay, so that's everything. And so the set of all those probabilities, okay, P1, P2, etc., Pn, is referred to as the probability distribution of X. Okay, so if we think of the example with the coin, okay, with the 2 coins, let's go back to that one. So your sample space, let's write it here. So sample space would be, 0, 1, or 2 heads. Does that make sense? But the probabilities that go with it, what should I write it here as? Yeah, I guess just probability distribution. Probability. Okay, so they are, okay, what goes with 0? A quarter, right? A quarter of the time you'll get 0 heads, right, which is up here, right? A quarter of the time, 1 out of 4, you get 0 heads, which is tail, tail. And then so let me join that together. So that goes with oh no, that's too thick, hang on. So that goes with there. right? And then the next one, so getting one head, you've got a half chance, yeah, okay. And then getting two heads, you've got again a 1/4 chance. Does that make sense? That's there, and then that's there. Okay, so that is like your probability distribution, basically. And so each of them you can see has to be between 0 and 1. It could be equal to 0 or 1, and it all adds up to 1. 1/4 plus a half plus a quarter equals 1. Okay, now your probability distribution is usually either given in table form, here we go, table form, graph form, or as a probability distribution function or probability mass function. And we'll do that in a bit more detail in the next exercise. Okay. Yep. And so actually let's have a look at this. Oh yes, down here we've got some examples of the language, which is quite important as well. And this is where, you know, questions can get a little bit tricky. So often we have to look at, you know, where does it sort of start and end. So if you want, for example, your probability, if you want the probability of your random variable to be 3, obviously it has to just equal 3. If it's less than 3, makes sense. Less than or equal to 3, you just have to be careful of. That means it can't be more than 3 or at most 3. So you just need to understand words like at most, more than 3 is more self-explanatory. At least is a tricky one, right? At least 3. So that means 3 or more. So x has to be greater than or equal to 3. You know, between 3 and 7, when it says that, that actually means it doesn't include 3 and 7. Okay. Okay. Some you get like this. It is at least 3, but no more than 7. So it's got at least 7. It's got to equal 3, but no more than 7. So it can be 7, but not more than 7, right? This one, x is more than 3. So it doesn't include 3. It's got to be bigger than 3, but no more than 7. So it does include 7. And then you've got here at least 3, but less than 7. So it has to equal to 3 and more, but it's got to be less than 7. So just be careful with the language. Let's do an example together. So this one says, magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% 3, 13% purchased 4, and 5% purchased 5. Okay, so what is the random variable? Like, what's the event here? The event is, like, it's the number of magazines sold, right? So let me just write it down for you. So random variable, capital X, is the number of magazines sold. Very straightforward. And part B, oh, actually, I should write out the actual numbers as well. Sorry, I should just put, like, you know, that is x equals 1, 2, 3, 4, or 5. Sorry, let me fix that. 4 or 5. It doesn't mention any percentage buying 0 magazines, so I think it's got to be 1 to 5. Okay. Part B. Let me just move this down. Part B says, make a probability table for the random variable. Okay, so let's say we've got, say little x is, remember, the actual number of, like, the event happening. So we could have 1, 2, 3, 4, or 5 magazines, like how before little x for us stood for how many heads. This time it's how many number of magazines that are being sold. And I should put down here then the probability. So probability of capital X, your random variable, equaling little x. Okay, you could put xi if you wanted to, I guess. Sorry, that's a bit small there. But for 1, what was it? 23%. So you could do it as a fraction, or you could do it as a decimal. I might write it in decimal, might be easier for me to write in. 23%, 38, so 0.38. 3 was 21%, so 0.21. 13%, 0.13, and then 5%, 0.05. Okay, there's your probability table for random variable. And then it asks us to, okay, I need to make some space. Actually, I'll just do it over here. Question C. Graph the probability distribution using a spike graph. Okay, I might switch to, is that on the same thickness? Yeah, I might switch to a thinner, sorry, pen. Might be a bit easier for me. So a spike graph was kind of like a column graph, except it just was a straight line going up. So along your x-axis, we're going to have like 0, 1, 2, 3, 4, 5. So like the actual sample space, right? Okay. And then, so I'll label that as X, and then on your Y-axis is going to be your probability. So you could just put PX up there. We can write probability. And what are our numbers ranging between? From 0.05 up to like 0.38. Oh, I should have spaced this better. So I might actually rub this bit out, make it a little bit taller. So I might make that, I reckon, 0.1, 0.2, 0.3, 0.4. I'll put here px equals x. Okay, so for 1, what have we got? 0.23. So there somewhere. Okay, and then for 2, 0.38. Where's 0.38? Somewhere there. Okay, please use a ruler. I can't do a ruler on the iPad. 0.21 here somewhere. And then 4 is 0.13, maybe here somewhere. And then 5, 0.05, that'll be like there somewhere. Okay, makes sense? And then let's do example number 2. And let me just move this down. Example 2 says show that the following are probability distribution functions. Okay, so this is a little bit of sneak peek into like the later stuff. So this is what we mean by over here. Here we go. The third way, okay, of representing a probability distribution is by a probability distribution function or a mass function. So here's an example. Px, which is your probability, x equals x squared plus 1 over 34. It just says to show that it's a probability distribution function, and it tells me x equals 1, 2, 3, and 4. Okay, so let's actually sub it in first. That'll give us the probability for each event, okay, for each one in the sample space. So if I put px, think of your function notation, so p1, so I'm just going to sub in 1 squared plus 1 over 34, so that's 2 over 34. Then we've got p2, so 2 squared plus 1 over 34, which is 2 squared is 4 plus 1 is 5 over 34. Let me shrink this down, and I'm going to move this down. Okay, then we've got p3, 3 squared plus 1 over 34, so that's 10 over 34. And last one, p4 equals 4 squared plus 1 over 34, so 4 squared, 16 plus 1 is 17 on 34. Now, if this probability distribution function is complete for this set of events, then these probabilities should all add up to 1. Okay, it needs to obey that rule. So let's check it out. So the sum of your probabilities of your events xi is equal to, and then you've just got to chuck it in the calculator for me, 2 over 34 plus 5 over 34 plus 10 over 34 plus 17 over 34. And it does add up to 34 on 34, which is 1, which is perfect, which is very good. Okay, so therefore, Px is a probability distribution function. You can also see as well that each of these are less than 1, aren't they? Yeah, it can't be, well, it could equal to 1, it just can't be more than 1, so that's okay, it makes sense. Okay, all good. Okay, let's do, B, I haven't got space for B. Let's do B. I'm going to move this, sorry. So B is very similar. I hope you may have, I hope you may have noticed something familiar with the notation. Hang on, let me come back to it. Okay, have a look up here for question B. Okay, I'm going to highlight in pink. This looks very familiar, right? This looks like when we used binomial theorem and we wrote out the, like the nth term in your binomial expansion. You've got the n choose r notation, or NCR up the front. And then you've got, your two events and to the powers of, however many times that occurs, for example. So we're just going to sub in again here and see what we get. So for P, it starts from 0 and goes to 3. So let's go P0 equals, now remember this is 3, choose 0. You've just got to chuck this in the calculator, use that C combination button. So then you have 0.6 to the power of 0. And then 0.4 to the power of, you've got to do 3 minus 0, which is just 3, right? Easy. Okay. If you like, I'll just put 3. 3 minus 0 we know is 3. Okay, and then you've got to do that on the calculator for me. I've already got it written down here for you, so it'll be quicker. So we get 0.064, I think. Right, so we're just got to go through P1. Actually, I should move this down. I won't have space. P1, so this time, remember 3, choose 1, or 3C1. So then we've got 0.6 to the 1. And then this is going to go down in power, squared. And remember the little trick, these powers have to add up to your n, right? 0 plus 3 is 3, 1 plus 2 is 3. Always has to add up to n. This one is 0.288. Then you've got P2 is 3, choose 2. So you've got 0.6 to the power of 2. Oops. And then you've got 0.4 to the power of 1, and on the calculator hopefully that'll give us 0.432. And then P3, last one, is going to be 3C3, or 3 choose 3, and you get 0.6 to power 3, and then 0.4 to power 0 technically, or you could just leave it out if you wanted to, and you get 0.216. Now, if you do a total of all of this, it should add up to 1. Okay, so therefore, it is a probability distribution function. Okay, I'll just skip writing that out so it's a little bit quicker. But yes, you can conclude there at the end. Let's do one more example. Let's say we've got 2 marbles are randomly selected. Let me change this back to green. Yep, 2 marbles are randomly selected. And without replacement, so that means they're kept outside of the bag. From a bag containing 4 red and 2 blue marbles, let X, capital X, denote the number of red marbles selected. Find the probability distribution of X. Okay. This might actually help if we just draw a bit of a tree diagram first so we can see what's happening. So you're pulling out 2 marbles out of the bag randomly without replacement. So what's your first event and what's your second event? Your first event is pulling out the first marble. So you could get red or blue. Makes sense? Okay, so the first marble or first choice is like the first event. Then your second event is just choosing your second marble, right? So you could get red or blue, and you could get red or blue. But we should write in the probabilities along the branches. So in your first marble, it's easy to figure that out. You've just got 4 red out of a total of 6 marbles altogether, right? So it's just 4 out of 6. And then blue is going to be 2 out of 6. You can simplify it if you want. I think it's easy to leave it like this at the moment so you can see where the numbers come from straight away. Now, if you've already picked, for example, a red marble, now remember there's no replacement. So what's your probability now of choosing a second red one? Well, there's only 3 left in the bag out of a total of 5 left in the bag. Does that make sense? So it changes to 3/5 now. Getting blue, however, you've still got blue in there, 2 blue ones in there, sorry, out of the 5. Now remember the other little trick I told you guys was the probabilities along a set of branches always needs to add up to 1 whole. So you can see here 3/5 plus 2/5 is 5/5, which is 1. Okay, 1 whole. Does that make sense? So let's just fill in as well down the bottom. So if I pick blue first and then red, there's still 4 reds left out of 5. If I pick a blue the second time, there's still 1 blue left out of 5. And that looks good. That adds up to 5/5, which is 1 whole. So you know you haven't made a mistake. So we could get red, 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 blue, blue, red, and then blue, blue. Let me just make this clear that this is a B. Okay, all good. Now we can work out actually the probability of each one. We did this actually way back in like year 10 probability. So if I'm getting red, then red, we go along the branch, and remember we multiply the probabilities. So 4/6 times 3/5 will give me whatever that probability is. Okay, and then to get red, blue, you just multiply along those branches. So that's 4/6 times 2/5. Okay, and then here we've got 2/6 if we get blue, and then red is 4/5. And then you've got 2/6 times 1/5. Okay, let me quickly, actually I don't need to calculate, I could do this. Because if I multiply that, that'll be 12 on 30, won't it? That'll be 8 on 30. Yeah, just multiplying fractions. Top times top, bottom times bottom. That's all I'm doing. Okay, so I get 8 on 30, 2 on 30. Okay, that looks good. Now it says find the probability distribution. So it's just the spread of all these probabilities. But it's probably easier just to put it into a table. So what are the events we're getting? And it tells us up in the question that X has to note the number of red marbles. So you could get 0, 1, or 2 red marbles, right? Does that make sense? Okay. So probability of X equals X. Okay. So getting no red marbles, which is blue, is 2 out of 30 over here. Getting 1 is either blue, red, or red, blue. So you've got to add those ones together. So that's 16 over 30. And then over here, 2 reds is 12 out of 30. There you go. Does that make sense? Now part B, so that was A. Let's do part B over here. Drawing a spike graph. Pretty straightforward. So you've got X. So what were our numbers? We could get 0, 1, or 2. So 0, 1, or 2. Some of these, they have the 0 on the x-axis, but you don't have to. I've seen it where it's not on the x-axis, like as in, sorry, at origin. That's what I meant to say. But I've done it without it, so you don't have to. It makes it a bit clearer, I think, for this one. Excuse me. Oh, if it's off the origin point. Okay, and then along here is your probability. And what do we have to go up to from 2 on 30 up to 16 on 30? Oh, I didn't draw this very well. Let's just go with, if I do up by 4s, would that work? If I have maybe 4 on 30 there, then it's 8 on 30. That's 12 on 30. And then that'll be 16 on 30, I think. Okay, let's do that. And then you've got 2 on 30 is 0, so that's halfway there. And then for 1 is 16. Okay. And then 12 on 30 for getting 2 red marbles. Okay. Hopefully that makes sense for you. Please have a go at the questions, Year 12, which is, let me write it down for you, what page number is exercise 23B, and it is on page 612. Please have a go, get a variety of questions done, and please check your work as you go along.